We'll be looking at lesson 4.1 in chapter 4 dealing with matrices today, and we'll start by looking at the very basic facts with matrices. They're just a rectangular array of numbers enclosed in brackets, and it can be used to display data from tables. It can be used to display real-world scenarios like we saw in chapter 3 with some of our systems of equations. So, just the very basic nomenclature and terminology. Every matrix is given a capital letter name so that you can refer to it. And when we look at a matrix, they have dimensions, and it's always listed by the row and then the column. So when we look, for instance, at example A, we can see that there are 2 rows and 3 columns. So this is classified as a 2 by 3 matrix. And we have various entries or numbers in that matrix, and each entry has its own address so that there is no confusion. And the address is listed by the lowercase letter that corresponds to the matrix. So in matrix A, you'll have the lowercase a, and then the subscript row and column. So when we look at this example, this tells us that this number that's given in red, the 16.206, falls in row 2, column 1. So it is A subscript 2, 1. When we look at this next page, if we would like to put, when you're given data right in a table, it's very easy to put that right into a matrix form. And certainly if we could do either a 3 by 2 or a 2 by 3 since we have those 2 dimensions, but the fact that it's already given to us the way it is, it's probably easiest to simply list it with 3 rows and 2 columns. And when we take a look at this, we want to know what the dimensions are. We can see that there are 3 rows in our matrix P, which I called P for price of the sandwich, and we have 2 different sizes or 2 different columns. So it's a 3 by 2 matrix. And if we want to look at what entry P sub 3(2) is, we can take a look at the 3rd row, 2nd column. And we know that that is 5.25. And what that represents is the price of a 9-inch tuna sandwich. And if we look at the next number that they give us in D, they say, well, what about entry 5.95? What would the address be? And we would use the lowercase p, and we would say, well, that occurs in row 1, column 2, so it would be P sub 1, 2. When we look at this next matrix, M, and we can see that's just a matrix where they've already given it to us in the matrix form. So if we look at this, we can see that we've got 3 rows and 4 columns. So that would be a 3 by 4. As far as the dimensions for matrix M. And if we want to know what the entry at M sub 3(2) is, we would go down to the 3rd row and then to the 2nd column. And we would see that, number 11 falls there. And, we can also see that 0 occurs at 2 places. First here in row 1 and then in row 2. So the address for the zeros in our matrix would be M sub 1, 4 for row 1, column 4, and then M sub 2, 3 for row 2, column 3. Okay, if we want to add or subtract matrices, we can certainly do that, and we subtract the corresponding entries in each matrix. So row 1, column 1, if we're adding 2 matrices, we would say row 1, column 1, and we would add that to row 1, column 1 of our 2nd matrix. And, so that's why it is the only way we can add or subtract matrices are if they have exactly the same dimensions, the same number of rows, the same number of columns. Otherwise, you can't do it, as you can see in these examples. Okay, if we go on to the next page and we see example 3, we're given 4 different matrices, A, B, C, and D. And if we want to, as we can see here in part A, add B plus D, and we can see that we have two different matrices, and I've listed matrix A, or matrix B, plus matrix D. Each of those are 2 by 3, so we know that we can add them together. We would start with 4 plus 0, and that would give us 4 in our resulting matrix. We would then go to our second entry, -1 plus 1 to get 0. And then -5 plus -3 to get -8. You then move down to the second row, 3 plus 3 to get 6, 2 plus 0 to get 2, and then 8 plus 10 to get 18. When we go to our next matrix B minus matrix A, I have B and A both listed here. We want to subtract A from B. When we look at that, we do not have that one-to-one correspondence because the dimensions are different. We have a 2 by 3 and a 3 by 2. So when we look at that example, we are not going to be able to add those together or subtract them because they don't have the same dimensions. When we look at our final example here, D minus B, those are both 2 by 3 matrices, so we will be able to subtract those. And when we look at that, once again, it's just we look specifically at the corresponding entries. 0 minus 4 to get -4, and so forth. 1 minus -1 is 2. -3 minus -5 gives us 2. And then you go to the second row and do the same thing. You just subtract them, and that's your resulting matrix. Okay, so when we look, we can certainly add, subtract. We can also multiply a matrix by a scalar. It's exactly what it sounds like, a scale factor, which we're used to using when we scale things up proportionately. You just multiply each entry within your matrix by that number or scalar. So, if you want to scale things up or scale things down, it's a great way to do it. So when we look at this, we're looking at shirt prices for t-shirts and sweatshirts. And if we want to display that in matrix form, we would look at it like this. And I called it C or S for shirts, since we're looking at different shirt prices. And when we look at this, we can, we have this example where we want to use a scalar product to find the prices of our t-shirts and sweatshirts if there's a 20% discount applied. So if you look at the way the book will solve these, quite often they will find 20% of those prices, which is a 0.2 scale factor or scalar times your matrix. That gives you the discount. That does not give you the sale price shirts, so you would then have to subtract that from your original matrix or your original prices. So that certainly is an accurate way to do it, but it takes 2 steps. You are scaling your matrix, you are then subtracting matrices. So, you can also do this in one step just by finding 80% of your matrix. So we can apply that 0.8 scalar to the matrix and do it all in one step. So either way is fine. I always like less work. So, when we take 0.8 times our matrix S, that's what we end up with, and our resulting, our resulting scalar product or matrix after being scaled is right here, and it shows the sale prices. So when we take a look at these next examples for simplifying matrices, it's just doing a combination of things. Adding matrices, scaling them, adding them, doing multiple things with the matrix. So when we look at part A, we can see 3B plus 2C. And when we look at that, it's just 3 times matrix B plus 2 times matrix C. We can certainly apply those scalars and multiply each number in each of those matrices by the scalar. But once we get that done, we're not going to be able to add those together. because they don't have, those matrices do not have the same dimensions. So, you know, there wouldn't really be any point, you wouldn't be able to do the entire problem. When we look at this, 2 times A minus 3 times C, in those, you know, both A and C are 2 by 2s, so we know we can do this. We can scale each of those matrices. We can then subtract, and, you know, here are each of those matrices scaled. And then we have our resulting matrix at the end after subtracting. In part C, we have D plus 0.5D, which certainly we can do because it's the same matrix, so it has the same dimensions. And you can take matrix D and then add 1/2 of matrix D. And when we see that, you know, once you have scaled the second matrix D, you then add them together and you get 9, -4.5, and 12. That's fine, but certainly, once again, we could do this in one step just by using a scalar 1.5 times matrix D and then getting the same resulting matrix. So our scalar product's going to be the same, it's just less work than it would be otherwise. Okay, and then when you look at the last page, you have, it's just showing the properties of equality for matrices. The commutative property, you know, we can certainly add matrices in any order and we will still get the same resulting effect. Associative property holds true for addition, and we can regroup and do them in different order. And then our additive identity, if you have a matrix, the same dimensions, but zero is all of the entries in that matrix, we're going to have the same matrix when you're done adding the additive identity to it. Our additive inverse, what you're looking at, the entries in that additive inverse are the opposite of what you have in your initial one, because when we add those together, you will end up with the zero matrix. So they are additive inverses. And we will be looking at that more in the next few lessons and using those properties. You can start the homework now.